We send nearly 200 billion text messages and emails a day, yet every time we hit that send button, we don't think much of it. After all, we trust in the encryptions protecting them, right?
Traditional key cryptography has long been a trusted method for securing data, using mathematical algorithms and hard-to-break keys to secure information. However, as technology advances, so do the tools and techniques available to potential eavesdroppers.
This is where the field of quantum cryptography comes into play. Instead of math, quantum cryptography utilizes the principles of quantum mechanics to keep messages safe, replacing numerical keys with photons or particles of light. Say that you want to initiate a new message to your good friend Quantum Quinn, but now with quantum cryptography. You start this process by sending over a stream of photons to create the key. As you're sending them, you put each photon through a polarizer, polarizing them into a certain state: vertical, horizontal, diagonal to the left, or diagonal to the right. When measured, each photon state represents a single bit of data, 0 or 1. For example, they could be something like this. As Quantum Quinn receives the photons, he doesn't know the particle's correct direction, so he randomly uses one of two beam splitters to translate each photon into bits. If he uses the wrong beam splitter, for example a diagonal splitter on a vertical photon, he will get a random bit. So it is crucial that his beam splitters match your polarizers. Eventually he will end up with a measured string of bits. Now you can both compare your values. You will compare the beam splitter he used with the polarizer you used to send the photons and identify which filters match. After this check is completed, you will discard the values of the photons read with the wrong splitter, and the remaining sequence is your encryption key. But how do you know that this is secure? Couldn't an eavesdropper just intercept the photons you're sending? Here's the thing, they couldn't do that without you and Quantum Quinn noticing. Since they don't know the photons' polarizations either, they too can only guess which beam splitter to measure with. If they measure with the wrong filter, they'll change the direction of the particle. If they then pass on their measurement result to Quantum Quinn, and it's a case where he used the correct filter, then his translated value will no longer be the same as yours, when it actually should be. You will then know that someone tried to intercept your message and can restart the process. Now you can safely send whatever messages you want, thanks to quantum cryptography, which has introduced a photon of new possibilities.